I'm going to do this question from the 2018 QAT exam, question 7. I'll just scroll through it so that you can write down the steps so you have a go at it before I tell you how to do it. Okay, there's another question on the next page. All right. Okay, so if we read the question, a student wishes to determine the value of the Avogadro constant experimentally. I spend about 10 minutes going through theory, so if you want to skip the theory, go forward about 10 minutes. So before we start looking at the question, let's go into a bit of theory about what Avogadro's number actually means. So Avogadro's number is the number of particles, a counting number, 1, 2, 3, how many particles are in 1 mole of particles, one group of particles. Okay, so how many particles? So there's kind of this particular technique, whenever you have an amount of something, there's 3 things you can talk about it. You can talk about how many particles there are, you can talk about what mass there is of those particles, and you can lump all the particles together and say how many moles. Do we have a whole mole or half a mole? Because a mole is a group. So any mass of particles, you can say 3 things about the same amount of particles. So when we were studying individual atoms are isotopes. So we were looking at carbon-12 to work out how big an individual atom was. We were looking at the fact that they gave carbon-12, that particular isotope, the number 12 exactly. And then everything else was relative. That's what the little r stood for, relative to carbon-12. So this particular isotope of hydrogen was pretty much 12 times smaller than carbon-12. And oxygen, this particular isotope of oxygen, was pretty much 16 compared to carbon's 12. So these were individual atoms of the elements. And then if we put all the isotopes together and got an average, the other isotopes of carbon-12, there weren't that many, the amount of them wasn't that many. So when you multiplied them and got the average, a weighted average, then the weighted average wasn't all that much different from this isotope, because this is the main one. And the weighted average of all the hydrogens wasn't that much different, and this is actually a 9. The weighted average wasn't all that much different from this main isotope. So these 3 isotopes were kind of the main isotopes, which is why the weighted average was the same. So this is to show you that an individual atom of carbon is 12 times bigger than an individual hydrogen. So we don't work with individual atoms, we work with a lot. So they use these numbers because carbon was pretty much 12 times bigger than a hydrogen. If you weighed out a group and we called our group 12 grams, then the number of atoms in 12 grams would be the same as the number of atoms in 1 gram of hydrogen, because each individual carbon is 12 times bigger than each individual hydrogen, roughly. So a group of carbon atoms that weighed 12 grams would have the same number of atoms in it as a group of atoms that weighed 1 gram. So this is a relationship between the mass and the mole of atoms. So the question is, we don't know in this mole, in this group, we don't know how many particles there are. And originally they didn't know. They just said, we'll use these. We know how big one atom is compared with another, and so we'll use those numbers and scale it up and have a group with the same numbers. So this group we'll call a mole, but we don't know how many actual atoms are in that. We don't know what Avogadro's number is. So to work out Avogadro's number, they have to be able to count individual, how many particles are in a mole. They have to count individual atoms. So when we do electrolysis, we are having individual electrons moving across from one electrode to another and being added. When we did our example, we did it with copper, being added to ions to make copper atoms, copper metal atoms. So if we can work out some way of measuring the number of electrons that moves across, we can relate that to the number of moles of copper. So for the first thing, we need to work out how are we going to work out the number of electrons, individual electrons. So when you measure the charge, the amps current is like a river. It's showing you how many electrons are flowing from one side to the other. So if you've got 2 amps, you've got a certain number of electrons flowing. So the longer that you leave them flowing for, the longer the time, the more electrons will flow. So if you multiply the amps by the time, then you'll get some number that is implying a flow of electrons. So we call this number, this random number that we get, we call them coulombs. So this is implying, like, it's a number that's showing the larger the number, the more electrons are flowing, but the number itself doesn't tell you how many electrons are flowing. So if you knew the number of the charge of one individual electron, then you'd be able to work out how many, divide that number into this number to work out how many more times, how much bigger charge it is, so how many more electrons. So if we look on your data booklet here, there's the charge on one electron. It's negative because electrons are negative, but this is how big the charge is. This is on page 5 of your data booklet. So once we know the charge of one electron, if you know the charge of a whole lot of electrons, so we work out the charge of a whole lot of electrons, like IT, and we know the charge of one electron from your data booklet, then if you divide that into however many, whatever charge you've got, you would know how many electrons were flowing, a counting number. So by using this, we work out how many electrons, the counting number, but we need to relate that number to how many mole. So just knowing the number of electrons doesn't really tell you how many moles of electrons or how many electrons are in 1 mole. You need to relate that to how many moles that you're deposited. So the way of working out how many moles of electrons we've added is to relate it to the way that we measure moles with the mass. So if you know the mass of the copper that you've added, you can turn that into the number of moles of copper. For every 1 mole of copper, you would have had 2 moles of electrons. For every 1 copper atom, you would have had 2 electrons. So for every 1 mole, you would have twice that number of electrons. So we can relate the number of electrons that we've added to how many moles of electrons we've added. So for whatever example that you do, if you work out those two things separately, the number of electrons and the number of moles of electrons, and divide them, then you can, when you divide anything, you're working out how many for 1 mole, and this will be Avogadro's number. Hopefully that made some sense. So to find Avogadro's number is the counting number of electrons or particles for every 1 mole. So how many particles for every 1 mole? So we need to work out the number of particles for a certain number of moles and then divide it to work out for 1 mole. And we're getting this, the counting numbers coming from the charge of electrons, and we know that moles were originally established with the mass. So we're relating the mass deposited to the number of moles of electrons. So we're getting these two parts separately. Okay, so the student has set their electrolytic cell up. So it's electrolysis they're doing, it's forcibly adding electrons with nickel. So nickel ions, it's a solution, so you've got water present, and you've got two electrodes, copper metal solid and nickel solid. So the first question is asking, what's the reaction that's happening? So first question, write the equation for the reaction that happens at the cathode. So we need to know which way the electrons are going. So we've got some water, the sulfate we ignore, it's not involved in the reaction, the nickel ions, and the copper solid and the nickel solid. So which way are the electrons going? Look at what's happening. So we've got nickel ions and water, and we've got water, copper metal and nickel. So the reduction at the reaction at the cathode is reduction. So we're looking for the reduction reaction. So the strongest, these are all reduction reactions. The strongest oxidizing agent is the one that undergoes reduction. So the nickel ions are going to gain electrons and turn into nickel metal at the, so it doesn't really, in order for you to get more of these, the power pack needs to be positioned to force the electrons this way. So if you steal the electrons from the nickel metal, then more nickel ions will be produced and you can form nickel metal on the copper cathode. Doesn't really matter what this is made from because the electrons will be forced onto here anyway. So even if this was going to undergo oxidation, the electrons would be forced back on. So the nickel metal will be building up around the copper. All right, so the equation that happens at the cathode is the nickel reaction, gaining the electrons to become nickel metal. Make sure, because this is in the electrochemical series, make sure that you put down the correct states. All right, determine the number of moles of metal that will be deposited on the cathode. Of cathode at the start, the mass of cathode at the end, so you just subtract that away and work out the number of grams that were deposited and work out the number of moles of metal that's deposited. Okay, this number of moles is going to be telling us the number of moles of electrons eventually. So we go from the mass of that to the number of moles of electrons. So now we need to work on how many actual electrons are being transferred. So determine the electric charge produced over a 10-minute period. So the electric charge is Q equals IT. That's how many electrons were moving. But what does 1200 C mean? Normally at this point, the next question is determine the number of electrons that are involved in the reaction. This is the number as in counting number. How many electrons? It doesn't say number of mole, it just says how many. So we know we've got 1200 coulombs, which is for a whole lot of electrons. If we know the charge on one electron, then we just divide the 1200 coulombs by the charge on one electron and we can work out how many actual electrons there were. So now we know how many electrons, and we know we'll be able to work out the number of moles of electrons in a minute, calculate the amount of moles of electrons that were transferred. So for every 1 mole of nickel that's transferred, you needed 2 moles of electrons. So it's a 2-to-1 relationship. So the number of moles of electrons is twice the number of moles of nickel. So if we multiply the number of moles of nickel by 2, we'll get the number of moles of electrons that were transferred. So now we know actually how many electrons, and we know that that is related to a certain mole, a lot less than 1 mole. So if we divide that into this, we'll get how many electrons for every 1 mole. So this is electrons, and I really should say electrons for every 1 mole of electrons, which is what Avogadro's number is. How many counting things for every 1 group of whatever it is you're counting. So you can see it's a bit higher than Avogadro's number. So the next question, which is lost, there it is. The next question says, compare the experimentally determined Avogadro constant with the theoretical value. So there's 2 marks for this question. So you need to number of electrons per mole. So the student's value is slightly larger. So whenever you're asked to compare things, it's either slightly it's larger or smaller, or make a statement comparing the 2 things, and then a reason. So for this number, when you divide this into this, for it to be too large, this number on the bottom would be too small. So for the number of moles of electrons to be too small, we worked out the number of moles of electrons based on the number of moles of nickel that was deposited, and we worked out the number of moles of nickel based on the mass that was deposited. So therefore, for this number to be too small, the mass deposited must have been too small, which means we probably dropped some, lost some at some point, which when you're doing electrolysis is what often happens. So some mass of nickel must have fallen off, so the mass of nickel goes down, the number of moles of nickel goes down, and therefore when you calculate the number of moles of electrons, it'll go down. Because it's on the bottom of the equation, it makes the number of moles of Avogadro's number go up.